Hello everyone, welcome to this lecture. The plan for this lecture is as follows. In this lecture we will introduce the notion of anonymous key exchange protocols, we will see the various definitions and we will see the underlying ideas involved behind the seminal key exchange protocol due to Diffie and Hellman. So, just to recap, the picture till now is as follows. Till now we had seen several powerful symmetry key primitives both in the passive world as well as in the active world. We have seen various notions of security like authenticated encryption, CCA security, CPA security. We had seen other primitives for integrity and authentications like message authentication code, and we had seen constructions of all these notions of security, namely we had seen constructions giving you this kind of security where the constructions are based on pseudo random functions, pseudo random permutations, strong pseudo random permutations and so on. So, basic fact about all the constructions that we had seen till now is that the security for all these cryptographic primitives that we have seen holds under the assumption that a common random unknown key is already agreed upon between the parties, specifically the sender and the receiver. So, now the question that we want to address here is that how a common random key is privately agreed upon over a public insecure channel, right. So, till now we were assuming that somehow the key agreement has already happened, and given that the key agreement has already happened, we saw how to design authenticated encryption schemes, CCA secure encryption schemes, CPA secure encryption schemes and so on. But now we would like to address the main problem, we would like to address the question that how at the first place itself a random key is privately agreed upon over a public and insecure channel, and this sounds like a classic catch-22 situation, right. So, because if you have a mechanism where sender and receiver can securely exchange a unknown key which is known only to the sender and the receiver over a public insecure channel, then using that mechanism they at the first place itself can do the secure communication also, right. So, what exactly catch-22 situation means, where you have a scenario where say for example, a fresh graduate comes out of the college and he applies for a job, and when the candidate faces the job interview, he faces the question that do you have any experience or not, but at the first place the candidate will get experience only if the job is given to the candidate. So, that is what we mean by catch-22 situation, and we are exactly facing the same scenario here as well. We know how to do secure communication, assuming that we know how to securely exchange the key over an insecure channel. So, that brings us to the problem of anonymous key exchange. So, let us define what exactly is the anonymous key exchange problem. So, the setting is as follows. We have a sender and a receiver, and we assume that somehow they know each other's entity, but they do not have any pre-shared information. So, you might be wondering that how it is possible for a sender and a receiver who are meeting for the first time that they know each other's entity. Later on we will remove this assumption as well, but for the moment to make the description of the anonymous key exchange problem simpler, let us assume that both sender and receiver know each other's entity. So, the goal here is to design a pair of protocols which I denote as pi s, pi sub s for the sender and pi sub r for the receiver, which are now interactive protocols, and the output space of this protocol will be some fancy k. And the goal is to design such a pair of protocols, one for the sender and one for the receiver, such that according to the individual protocols, sender and receiver communicate over an insecure channel, and at the end of the protocol, at the end of their respective protocols, sender and receiver output some respective keys. So, the output of the sender I denote as k sub s, and the output of the receiver I denote as k sub r, and we assume in this problem definition that we have an eavesdropper, a computationally bounded eavesdropper, who is getting access to the entire communication that is happening between the sender and the receiver. So, the adversary is aware of the pair of protocols using which the sender and the receiver are interacting, namely it knows the steps of pi sub s and pi sub r, and it also gets access to the information that is exchanged between the sender and the receiver, which we call as the protocol transcript, and which I denote as tau sub pi. And notice that this protocol transcript is going to be a randomized variable, because the information which sender and receiver are going to exchange, they will depend upon the internal randomness with which the sender and the receiver are going to invoke the respective protocols pi sub s and pi sub r. So, it is not the case that sender and receiver will exchange the same set of values every time they invoke this protocol pi, because they are invoking a randomized protocol. Now, the properties that I require from this pair of protocols pi sub s, pi sub r are as follows. The first property is the correctness probability, which says that with very high probability the individual outputs of the sender and the receiver should be the same, namely the output k sub s and the output k sub r should be same. And now we can have two variants of security which we can demand from these protocols pi sub s and pi sub r. The first definition is a weaker form of privacy, which I call as weak privacy, which requires that with very high probability a computationally bounded adversary, even after knowing the protocol transcript, does not learn anything about the output of the sender and the receiver. So, in here I am not demanding security in the indistinguishability sense. Here the demand is in the sense that either the adversary should not learn the entire ks and the entire kr. It is fine if the adversary learns something about ks and sub r, ks and k sub r, but the requirement here is that as in its entirety the outputs of the sender and the receiver should not be learned to the attacker. Whereas we can go for a higher notion of security, which I called as stronger privacy, which demands that from the viewpoint of the adversary, even if the adversary has access to the protocol transcript, from the viewpoint of the adversary the respective outputs of the sender and the respective output of the receiver should be computationally indistinguishable from a uniformly random element of the output key space fancy key. So, that is a more stronger notion of secrecy, because here if we go for this stronger notion of secrecy, then it is not allowed that adversary learns something about the respective bits of k sub s and k sub r. From the viewpoint of the adversary, the respective outputs of the sender and the receiver could be any candidate element from the underlying key space fancy k, right. So, we will see constructions satisfying both the weaker form of privacy and the construction satisfying the stronger form of privacy. You might be wondering that why exactly we care to achieve weaker form of privacy. So, that will be clear later on. Looking ahead, we will see constructions achieving weaker form of privacy based on cryptographic assumptions which are mild, whereas if we want to achieve key exchange protocols which achieve stronger notion of privacy, then we have to go for cryptographic assumptions which are slightly stronger. So, we had seen intuitively what exactly weaker privacy and stronger privacy means. So, now let us go ahead and model these requirements formally by an indistinguishability based game. And while giving the indistinguishability based definition, for simplicity we assume that we are considering key exchange protocols which has 0 correctness error. That means with probability 1 the output of the sender and output of the receiver will be the same. So, we are considering that kind of key exchange protocols. So, let us see first how to model the weak privacy, and remember the requirement of the weak privacy is that even if the adversary sees the whole transcript exchange between the sender and the receiver, the resultant output key which is obtained by the sender and the receiver should not be learned or should not be known to the adversary in its entirety, and that we model by this game. So, this game we call as key exchange, and the superscript WEV, EAV denotes weak eavesdropping or weak privacy here. The game is played between a challenger and a polytime adversary, and what the challenger or the experiment does is basically it simulates a random instance of the key exchange protocol pi. So, the protocol pi is basically the pair of protocols pi sub s and pi sub r, where the pi sub s protocol is going to be invoked by the sender and the pi sub r protocol is going to be exchanged by the receiver, but as a collection we call it as a protocol pi. So, the challenger basically simulates a random instance of the protocol pi by playing the role of the sender and the receiver in its mind with their respective coins as per the protocol pi, and it denotes a transcript tau. Now, what it does, it throws a challenge to the adversary, namely the transcript, and this models the fact that in the real world the adversary sitting between the sender and the receiver would have observed the transcript which is generated by the sender and the receiver by running the protocol pi. Now, the challenge for the adversary is that by seeing this transcript tau, it has to figure out what exactly is the value of key k which sender and receiver would have obtained by running with respect to this protocol tau. So, basically the adversary has to respond with a key from the key space, which I denote as k dash, and the security definition and the way we define the output of the experiment is as follows. We say that the adversary has won the experiment, if and which is also denoted by saying that the output of the experiment is 1 if and only if the guess of the adversary k dash is exactly equal to k. That means the output of the adversary, that means the adversary A, without knowing the internal randomness of the sender and the internal randomness of the receiver, and by just observing the protocol transcript tau, is able to come up with the exact key k which sender and receiver are going to obtain by running with respect to this protocol transcript tau. If that happens, then we say that the output of the experiment is 1, and the security definition is, we say that the protocol pi, the key exchange protocol pi, has weak privacy if for any polytime adversary participating in this experiment there exists some negligible function such that the probability that adversary wins the experiment is upper bounded by some negligible function, where the probability is taken over the random coins of the challenger, namely the random coins with which it is simulating the role of the sender and the receiver. So, notice that here the adversary does not have to distinguish between something, right. The goal of the adversary is to come up with the key which the sender and the receiver are going to obtain with respect to the protocol transcript tau. That is why in the security definition we do not have an expression of the form that the adversary's chances of winning the experiment is upper bounded by half plus some negligible function. The goal of the adversary is to come up with the exact k with which sender and receiver are going to obtain by running the protocol pi, and which is consistent with the protocol transcript. Also in this definition, we allow the adversary to win the game with some negligible probability, because there is always a guessing adversary who can just guess some candidate key k dash from the key space, and with non-zero probability it may turn out that that key k dash is exactly equal to k. So, now let us see how we can model strong privacy. And remember, the goal of strong privacy is that an adversary who monitors the transcript exchange between the sender and the receiver should not be able to distinguish the resultant key which sender and receiver are going to obtain from any uniformly random element from the key space. And again, for defining this modeling the strong privacy, we assume key exchange protocols where there is 0 correctness error. This is again without loss of generality. It is very straightforward to incorporate this condition as well in the security definition. So, now the experiment is called EAV, because now we are not modeling weak privacy, we are now modeling strong privacy here. And the rules of the game is as follows. Rules of the game are as follows. The adversary is waiting for a challenge here, and the challenge is again generated more or less in the same way as it was generated in the experiment for weak privacy, namely the challenger here plays the role of the sender and receiver in its mind and invokes an instance of the protocol pi sub s and an for the sender, and an instance of the protocol pi sub r for the receiver with their respective randomness, and it generates a protocol transcript tau. That protocol transcript is now given as a challenge to the adversary. So, this models the fact that the adversary sitting between the sender and the receiver would have eavesdropped and obtained the protocol transcript tau pi. And now, since we are trying to modeling the indistinguishability based notion of security for the key in the context of key exchange protocol, the challenger additionally throws a challenge as follows. It tosses a fair coin with probability 1 by 2 it could be 0, or with probability 1 by 2 it could be 1. And now, apart from the transcript, right, depending upon whether the coin toss is 0 or whether the coin toss is 1, the challenger either submits a random element from the key space to the adversary, or the key k which the sender and receiver would have obtained by running the protocol instance in the challenger's mind. Now, adversary A does not know whether the value from the key space that it is seeing is a random element from the key space, or whether it is a key which the sender and the receiver would have obtained by running the protocol and by running the protocol pi and obtaining the transcript tau. So, the challenge for the adversary is to generate whether he is in the method b equal to 0 or whether he is in the method b equal to 1, and it submits its response, namely a bit. And the definition here is, we say that the adversary wins the experiment, which is also denoted as that the output of the experiment is 1 if and only if adversary A could correctly identify whether he is seeing an element as per the method b equal to 0 or whether he is seeing an element from the key space as per the method b equal to 1, right. And the definition of strong privacy here is we say that key exchange protocol pi gives you strong privacy if for any polytime adversary participating in this experiment there is some negligible function such that the probability adversary wins the experiment is upper bounded by some half plus negligible function. So, now this is different from the this definition is different from the weak privacy, because in the weak privacy the goal of the adversary was to come up with the exact k which is consistent or which would have been obtained by the sender and the receiver as per the transcript tau. But now here the goal of the adversary is to distinguish the k which sender and receiver are going to obtain as per the protocol transcript tau from a uniformly random element from the key space. So, that is why now we are having an condition which similar to the indistinguishability based definition. And again we are putting this condition half plus negligible because there is always a guessing strategy by the adversary with which the guessing strategy of the adversary will be just to guess whether he is in the method b equal to 0 or whether he is in the method b equal to 1, and the success probability of that guessing strategy is 1 by 2. Apart from that, we are willing to let the adversary win this experiment with some negligible function because we are in the computational world. An equivalent formulation of this notion of strong privacy is that we say that the protocol key exchange protocol pi gives you strong privacy if for any polytime adversary participating in this experiment the distinguishing advantage of the adversary is upper bounded by some negligible function in the security parameter. That means, it does not matter whether the challenger has generated the challenge by the method b equal to 0 or whether he has generated the challenge by method b equal to 1. In both the cases the response of the adversary should be almost the same, say b dash equal to 1 except with some negligible probability, and we can prove that both these conditions are equivalent to each other. Namely, if you have a key exchange protocol satisfying the first condition, then it also implies that it satisfies the second condition and vice versa. So, depending upon our convenience we can use any of these two conditions. So, now we have the definitions of prior key exchange, we have the security definitions of key exchange protocols, and now you might be wondering that whether indeed it is possible to design key exchange protocols where sender and receiver without having any pre-shared information can do some communication over a publicly known insecure channel and end up agreeing upon a key which is not known to any third party. So, on a very high level it might look like an impossible task, because how it is possible that as unknown sender and receiver who just know their identity and have no pre-shared information whatsoever can do public interaction and agree upon something which is known only to them. But it turns out that we have some such key exchange protocols, and this is due to the base of this such key exchange protocol is the pioneer work by the Diffie and Hellman, who were the first people for the first pair of cryptographers who came up with their seminal key exchange protocol. So, in this lecture we are going to see the underlying idea based on which their key exchange protocol was developed. So, before that, let me tell you some fascinating history about how exactly their key exchange protocol came into existence. So, Whitefield Diffie were very interested in solving the key exchange protocol or key exchange problem, and he strongly believed that indeed it is possible for a sender and the receiver to do public communication and agree upon a common secret key. And in 1974 he gave a seminar at IBM's Watson laboratory to a skeptical audience who were not buying his idea that indeed key exchange is possible over public channel. The only positive outcome which came out of that seminar is that he came to know that it is not only him, there is another person, a professor at Stanford called Martin Hellman, who is also working on the same problem and trying to come up with public key exchange protocols. And as soon as Diffie came to know about this, he started some 5,000 kilometer odd journey to meet and pair up with Martin Hellman, and that is how they started their work on coming up with a protocol for solving the key exchange protocol, and they worked 2 years rigorously, and finally they came up with their groundbreaking Diffie-Hellman key exchange protocol. So, let us try to understand the underlying idea which is there in the Diffie-Hellman key exchange protocol. So, the basic idea behind their key exchange protocol is that there are several tasks in this world which have asymmetry. or they are asymmetric in nature. And asymmetry in the sense that they are very easy to execute, that means those actions, certain actions are very easy to execute, but extremely difficult to reverse. So, what I mean by that is, imagine I give you a padlock in an open state, and if I ask you to lock it, then you do not need any key, you just have to press the head of the padlock, and from the open state you can easily take it to the locked state. But now if I give you the key padlock in the locked state and I ask you to take it back to the open state, then it will be extremely difficult for you if you do not possess the key for the padlock. So, in that sense, this you have an action here where going from one state to another is extremely easy, but going back from the obtained state back to the original state is extremely difficult. It is not impossible, remember that I am saying it is extremely difficult to go back or reverse the action if you do not know the key. There might be other methods to reverse the action without the key, but those alternatives will be extremely difficult. In the same way, consider this task that you are given a publicly known color, and say if you want to prepare a secret mixture, right, then it is very easy for you to do that by taking that publicly known color and adding to that existing color a secret color and then obtaining the mixture. So, preparing the mixture is very easy for you, but if someone gives me this mixture and does not tell me what exactly was the secret color which was added to the public color to obtain this mixture, then it will be very difficult for me to find out or separate out this mixture into its constituents, namely the publicly known color and the secret color which I have added here. So, in that sense, preparing a mixture is easy, but separating out the mixture to its individual components is an extremely difficult task. Again, I stress, I am not saying it is an impossible task, I am saying it is an extremely difficult task, it is very time consuming. And finally, it is very easy to break anyone's heart by just saying some bad words, but once someone's heart is broken, then it is very difficult to win or convince to win back the love and the confidence of that person. In that sense, this going from this state to this state is very easy, but going back is extremely difficult, right. So, based on this idea, Diffie and Hellman thought of several ideas that how exactly they can solve the key exchange protocol, and when they came about this idea that there are certain tasks which have asymmetry involved with them, then based on that concept they thought of this idea of solving the key exchange protocol. So, we are not going to see the exact mathematical details of the Diffie-Hellman key exchange protocol, which those details we will discuss in subsequent lecture. I am just trying to give you the intuition that what exactly was the underlying idea here. So, the goal here is for the sender and the receiver to agree upon a common random secret mixture, color mixture, which will be known only to the sender and the receiver who have no pre-shared information to begin with. So, here is how the protocol will proceed. Both sender and receiver will start with some common color publicly known, and what they do is they individually prepare some random secret mixtures by adding a secret color independently picked and adding it to the publicly known color, right. So, both of them are independently taking the secret colors and preparing a mixture, and once they obtain their respective mixtures, what they do is they publicly exchange their mixtures with each other over some public channel, right. And when these mixtures are exchanged, we assume here that the mixture separation is extremely time consuming, extremely difficult, it is a computationally heavy task. That is an assumption I am making here. Okay. Now, once both sender and receiver obtains their respective mixtures, what they do is to the mixtures that they have obtained from the other party, they add their respective secret colors with which they started the protocol. So, for instance, sender on receiving this mixture, it takes a secret color and adds to it, and in the same way the mixture that receiver has obtained from the sender, which is the sender's mixture, receiver adds its own secret color. And now you can see what both sender and receiver are going to obtain. Both sender and receiver are going to obtain a final common mixture, because this final common mixture is a mixture of three colors: the publicly known color, the sender's secret component and a receiver's secret component. It does not matter in what order you mix them, irrespective of the order in which you mix them, the resultant mixture is going to be the same, and that ensures that both sender and receiver are going to obtain a common mixture, right. And now why it is secret? It is secret because we are assuming here that when sender and receiver are exchanging their respective mixture separation is extremely time consuming. That means, if there is an eavesdropper who is actually monitoring the communication happening between the sender and the receiver, and it knows the entire description of the protocol step. What the adversary does not know, it will not know the exact secret components which the sender and the receiver have individually added. And even after seeing the mixture which sender and receiver are exchanging, it will be difficult for the adversary to separate out or find out the respective things which the sender and receiver have added. And that ensures that the final mixture which sender and receiver are agreeing upon is already a secret color or a secret mixture which will not be known to an eavesdropper. So, that is a fundamental idea behind the Diffie-Hellman key exchange protocol. So, of course, this is an idea behind the key exchange protocol. Now, we have to convert this idea into an algorithm, specifically a mathematical algorithm. So, what we are going to discuss now is how we can convert this idea of exchanging colors and coming up with a common secret mixture known only to the sender and the receiver into a key exchange protocol with weak privacy, right. So, this is I am retaining the blueprint of the key exchange protocol based on exchanging color mixtures. And now what we have to do is we have to come up with an instantiation or replacement of each of the steps where colors are used, mixtures are prepared and exchanged and so on by some mathematical step. So, to instantiate the idea, our idea what we need here is we need some special functions which I denote as big E and big F. So, the function E is from the set fancy x to fancy y. So, it is a one input function, whereas the function f is a two input function taking two inputs from the fancy set x and giving you an output from the fancy set from the set fancy y. The requirements from the functions are as follows. So, the function E should be easy to compute, and the second requirement from the function E and function f is that if you are given any alpha from the domain of the function E and the value of the function E on any value beta, then even without knowing the value beta, just based on the knowledge of alpha and the function output of E on the value beta, it should be easy to compute the value of the function on the input pair alpha comma beta, and this should hold for any alpha comma beta. That means, if you know beta and if you know the value of the function E on an unknown input alpha, then even without knowing alpha, it should be easy for you to compute the value of the function on alpha comma beta. And finally, since we are aiming for weak privacy, we require the following property. We require that if someone knows the value of the function E on an unknown alpha and an unknown beta, then it should be very difficult to find out the value of the function f on the value alpha comma beta. So, these are the properties which I require from the functions E and f, and it is easy to see that altogether all these properties automatically imply that my function E should be one way function. So, remember we had already discussed what exactly is a one way function long time back. A one way function informally is a function which is easy to compute on any value from the domain, but computationally very difficult to invert for random values from the range of the function, right. So, it is easy to see that all these implications imply that a function E should be a one way function, because if the function E is not a one way function, then given E of alpha it will be easy to compute alpha, and given E of beta it will be easy to compute beta, and automatically if you know alpha and beta and the description of the function f, then you will be able to compute the value of f on alpha comma beta, which goes against the requirement that it should be difficult to compute f of alpha comma beta if you are just given the value of E alpha and E of beta. But not only we require the function E to be one way, it turns out that we need some additional properties as well, namely the property that we require here is that if you know alpha and the value of E on the input beta, then even without knowing beta it should be easy for you to compute f of alpha comma beta, and in the same way without knowing alpha, given just E of alpha and beta, it should be easy for you to compute f of alpha comma beta. So, these are now additional requirements on this one way function. Later on we will see exact instantiations of this function E and f, but for the moment assume we have such functions E and f, and now let us see how exactly we can convert this color based protocol into a concrete key exchange protocol. So, assume the public setup, namely the public color here which is known both to the sender and the receiver, is nothing but the description of the function E and the description of the function F. Now, what the sender and the receiver has to do, they have to prepare their respective secret mixtures. So, what they do is sender picks a random alpha from the X set and computes E of alpha, and independently receiver picks a beta from the set X and computes E of beta, and they exchange the values of E of alpha and E of beta over a public channel. And now I am assuming that even if there is an adversary who sees the value of E of alpha and E of beta, since a function E is a one way function, it will be difficult for an adversary to find out what exactly alpha and beta are. That is what is the property I am assuming from the function E. Now, once E of alpha and E of beta are known to the sender and receiver respectively, again by using the fourth property from the function E and F, we can see that it is easy for both sender and receiver to compute f of alpha comma beta. Why? Because sender is now knowing E of beta and it has alpha. So, using the knowledge of E of beta and alpha, it can obtain f of alpha comma beta, and in the same way receiver, it is now learning E of alpha. It is fine, it does not know alpha, but given beta and E of alpha, it can compute f of alpha. And now you can see that f of alpha comma beta is a common value from the set fancy y, which is known both to the sender and the receiver, but it will not be known in its entirety to any eavesdropper, and that comes from the fact because the function E is a one way function. Now, if you want to obtain a key exchange protocol with a stronger privacy notion, namely the strong privacy where the resultant key should be indistinguishable from any potential key from the key space, right, then we can retain the same blueprint of the Diffie-Hellman key exchange protocol that we have seen just now, namely sender and receiver picking respective alpha comma beta and exchanging the values of E alpha and E beta. What we have to just do now is to ensure that the resultant key, namely or the resultant value, namely f of alpha comma beta, is a computationally indistinguishable value from the viewpoint of an eavesdropper. We need now some more stronger properties from the function E and from the function f. Namely, the requirement of one wayness is still there. The function E should be easy to compute, but difficult to invert on random values from the domain. And again, given alpha and the value of E comma E of beta, it should be easy to compute f of alpha comma beta for any alpha beta. And now, the stronger property that I require from the function E and f is that for every random alpha comma beta, the value of alpha comma f of alpha comma beta should be computationally indistinguishable from any random value y from the set fancy y. So, this requirement was not there when we were aiming to design the Diffie-Hellman key exchange protocol with a weaker notion of privacy, because there the requirement was that adversary should not learn f of alpha comma beta even if it knows E of alpha, E of beta. But now, since we are aiming for a stronger privacy notion, we are putting additional requirements on the function E and f. Namely, we require that even if someone knows E of alpha, E of beta, the value of f of alpha comma beta for that adversary or for that person should be computationally indistinguishable from any random value from the set fancy y, right. And if we assume that indeed our function E and f satisfies this requirement, this additional requirement, it is easy to see that the same protocol which we had just seen giving us the weaker privacy notion ends up giving us a stronger privacy notion. We do not have to add additional step, we just have to make stronger assumptions about the functions E and the functions f. So, that brings me to the end of this lecture. Just to quickly summarize, in this lecture we have introduced the problem of key exchange protocol. We introduced the key exchange problem where the goal of the sender and the receiver is to interact publicly over an insecure channel with no pre-shared information and end up with some common output which is known only to the sender and the receiver, but unknown to any third party. And we have introduced two notions of secrecy for such key exchange protocols, namely the notion of weak privacy and the notion of strong privacy. Thank you.